All right, week 7, here we are. The topic of today, and most likely next week as well, is going to be sequencing. So putting our various sound-making tools into a rhythmic structure so that we can, create rhythms, melodies, and basically structure things in time. And I've got chapter 5 here printed out. I'll put that in the library sometime tomorrow, probably. And I've also prepared some code ahead of time today. So I have 2 buffers that I am reading. I'm using a slightly different technique. I'm using resolve relative instead of this process.now exceeding path. I think resolve relative is in the book. It's basically just a different way of doing the same thing. So this is a PVC pipe and a glass bottle. And then I have 2 synth we'll improvise a little bit with how we use these. I just wanted to give ourselves some material to work with. This is a basic sort of enveloped panned sine wave generator. So we have a sine wave which is panned from 1 to 2 channels. There's an envelope that controls the amplitude, and that's it. And then this one is a sampler, so it plays a 1-channel buffer with a flexible rate, goes through a low-pass filter, gets panned, and it also has an envelope which is applied to the amplitude. So it's just basic stuff here. So here's our sine wave. Right? We can do all sorts of things with that, change the frequency, change the envelope. And then here's the PVC. It's just me smacking my hand on the end of the PVC pipe. And then here's the bottle. So, various things we can do. Slow it down, pan it left or right. Yeah, get the idea. All looking good, right? Familiar stuff. Right. So there's the way I like to start talking about sequencing is with a class called routine. So a routine is described in the help files as a function that can return in the middle and resume where it left off. So as an example, a routine can be used to take a function which plays several synths to create a chord or just a cluster, and it enables you to basically space those out in time. So that's a very simple use of routine, and I think it's probably a good place to start. So let's start by building a function. Let's use the bottle, I guess. I was sort of messing around with the PVC earlier, and now I'm feeling bottle vibes. So all we really have to do here is say samp, and the buffer we're going to use is the bottle. And let's try to make sort of a chord out of this first. So I'm going to soften the attack and slow it down quite a bit by 20 semitones. And I think I have the amplitude defaulting to some low value just for safety, but I think we have a little bit of room to play with here. Right, or maybe. Okay, so I'll just copy this a couple times, and we'll do something like this. Right, so if we've created this function called f, not really good function design. I mean, it just plays this one chord. We haven't declared any arguments. We haven't made it flexible, and we probably could express this more concisely with iteration, but it's a starting point. So we know from a couple weeks ago that we can evaluate a function like this, and it will perform the contents of its function. And as far as the computer is concerned, these things are not really happening simultaneously. They're just happening so fast, one after the other, that to our musical ears, they might as well be happening simultaneously. So very normal question to ask is, okay, how do I make a melody out of this? So the way we do that is we create a routine, and I'm going to do this kind of step by step. A routine is, let's just build a very, very basic routine first. Say R equals routine. So a routine just takes one argument, one input, and that is a function. And that function can contain yield or wait calls, Y-I-E-L-D or W-A-I-T. And when you use those method calls on a number, they mean the same thing. So here's an example. We will post the number 0, then we'll say 1.wait, then we'll post the number 10, and then we'll wait for 2 seconds, and then we'll post the number 100. And that's our routine. Okay, so this is like as simple as it gets. And routines have basically two modes. I like to think routines have two modes, manual mode and automatic mode. So in manual mode, the way we interact with routines is we call next on them. So we've defined this routine, and now we say next. And we look at the post window, and the very first thing that happens is, well, it sort of looks like two things have happened. First of all, we have posted the 0. That's the first thing we encounter, and then the routine encounters a wait. And in manual mode, when we're using next, the routine actually returns the value to which wait is applied. And it's the same thing if we use yield. I think in this context, it sort of makes more semantic sense to use yield because the routine is yielding the value to us. It's sort of passing control back to the user and saying, okay, I did what you wanted, and now I am yielding 1. So I posted 0, yielding 1. And now once we've called next the first time, we can call next again. And now we will see 10 posted in the post window, and then we will see the number 2 returned in the post window. Right? And then if we call next again, we will see 100 posted to the post window. And then there's nothing left. There's no more yields, and so the routine says, I have the absence of things. I have nil for you. So this is a pretty silly example because it's, what exactly, what are these numbers doing here? Why do we want to return 1 and then 2? It's really just a sort of abstract demonstration here. So let's go back to this example and bring it down here. So what we'll do is we'll build this function and we'll say 1.yield, and then we'll bring it, copy, and bring it here. And we don't really need to yield at the end. Sometimes this is consequential, like if you're going to use a routine to play this and then play something else, like 2 melodies which each have 4 notes. If you didn't have this yield at the end, it would play, wait, play, wait, play, wait, play, and immediately go on to the very next thing, right? So, we'll put a yield here anyway. So now we've created this function. Now we cannot evaluate this function like this. This won't work. I mean, it does the first thing, and then it says it runs into a 1.yield, and the problem is that we are outside of a routine. And outside of a routine, you just cannot yield or wait. These are just not allowed.
So
yeah.
The method both yield and wait, they will only work inside a routine.
That is correct. Okay. Yeah, I mean it's one. Yeah. So the question is yield and wait. They always work inside of routines. There are other types of objects with which implicitly create a routine, and so yield and wait can be used in there as well. But generally, yes, you have to be inside of a routine or a routine-like process. So what we do, instead of just calling the function here, is we make a routine out of f, right? So we already have our function, so we just plug it in, and there we go. And now we can say r.next. And so we will hear a sound and see 1 in the post window because we are returning the, Then we get to the end, and it's nil, 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 nil. You can reset a routine at any time, and you could think of this as like a tape player, and we're just rewinding it back to the beginning. So we can reset, and even in the middle, we can reset, and, right, back to the beginning. And right, so this is here's a manual mode basically, and if we want to put this routine into automatic mode, just have it treat these yielded values as durations to wait. Again, it doesn't matter if you say yield or wait. These are, I don't think I've ever encountered a situation where they are not interchangeable. But in automatic mode, when you're playing the routine, it just sort of looks more correct because these are actually being treated as a pause. So we'll actually bundle these into one clump of code here. So we make our function, and we create a routine from that function, and then we can say r.play. And off it goes. It gets to the end, you can reset, and we can, manual mode a little bit, reset, and if we want to automatic, we just play it. So this is a simple example of routine as a musical sequence generator. And in this case, it's the stuff in between the wait/yield calls that we actually care about. That's where the business gets done, if you know what I mean. It's when we next through one of these routines, like that produces sound, the yielded values they don't actually matter. I mean, they could actually be like a string, I think. Like if we do it something like this. Oh, it doesn't like that. I think maybe it does have to be a number. But it could be a 0, right? It could be a million. It doesn't really matter. It's just kind of a side effect of routine's behavior here. Right. Now, before we move on to routine as like a data generator, I do want to point out that this, we can express this routine in a more succinct way, specifically using iteration. So as you can see, this is a really repetitive routine. We're always waiting for the same amount of time, and each synth call is nearly identical. The only difference is the playback rate. So let's rewrite this. Actually, maybe you want to have sort of a 30-second brainstorming set. Like, what would this look like? How would we use, if this was a question on the homework or something? How would you approach rewriting the contents of this function using iteration?
An array, collect.
Yeah.
And then have rate be the things held in the collect.
Good. Yeah. Array.collect, and then the rate is. So we're going to dump these numbers right into this array. So we'll just pop them in there. Good. Right, so we are going to collect, or do would also work here. Collect is fine too. And we're just going to take one of these, put it in here, put one of those in there, get rid of all of this. And we just, instead of a number here, we're going to say rate. And that should do it.
1 second in between all of them.
Right. When under default conditions, it waits for 1 second. Technically, this is when you yield inside of a routine, it's not measured in seconds, it's measured in beats. It just so happens that the default scheduling mechanism is set to a tempo of 60 beats per minute. So seconds equals beats. So it's, it's technicality here, but just something to keep in mind. This is actually a duration in beats. Yeah. Right, and so now we have all sorts of fun things we could do. As an example, as a variation, we can change this a little bit, right? And let's actually bring this into we can just play it right here, right? There's really no problem in just playing the routine right after we create it. Yeah, so we're getting more of like a strum arpeggiation thing. Here's an idea. What if we wanted to sort of do this sequence, like a sequence within a sequence? Like we want to do this one sequence, which is 4 notes, but then do it again, like a half step higher, and then again a half step higher, or something like that. So we can nest iterations. Yeah. So this is a little bit of a brain teaser here, but let's make a variable called shift, which is initially 0. Well, you know what? Let's just okay. Let's just do iteration within iteration. I think that's going to be easier. So we'll do 0. 0, 1, 2, 3. We could collect over this, and we'll call this a shift amount. Right? So shift is going to be 0 on the first time we perform this iteration, and we're just going to add it to rate. let's try to make this look a little nicer. Sorry? Okay. Let's see if I've missed anything here. So yeah, the outermost collect, it's going to happen 4 times. And on the first time, shift is 0. So the rate is just going to be these 4 numbers, and we play a synth and wait for a small amount of time. And then again, we do it again, half step higher, half step higher, half step higher. Yeah. We can randomize this. Yeah, lots of variations here. All of these parameters can just be made into random values here. And because they're all inside of these iteration functions, so each time a synth happens, it's part of a new performance of that function, a new performance. So yeah, so some of the attacks are softer than others, and you get the idea. If we want a routine to play forever, we can just copy this, just so I save all my variations here. We will just say, I think we can just say inf.collect. That's one way to do it. We don't want to do shift here, because then the pitches are going to keep going up and up and up and up. So we'll just go back to this version here. But we just have this process, which I think this will work. No, it doesn't like that. I think inf.do will work though. I think the reason is I don't want to just make stuff up here. It might be the case that you know what? It's probably some back-end design thing, which is but there's even another way which is just as good, which is to just say loop instead of inf.do. Let's replace that with loop, and then it will do this forever. I'm going to change this back to 0.2 and change this back to 0.01 and make this 2. Yeah, you need to stop it, you can hit stop. Command period will work. The stopping and clearing stuff off of routine schedulers is one of the side effects of command period, but you can also just stop a routine manually. And you can't play it again because it's at the end. Well, actually, it's not really, it doesn't have an end, but once you stop a routine, it can't be restarted. I think you have to actually reset it.
It's eliminated from the node.
I'm not. I think once you stop a routine, think of it as like a hard stop. Like you've kind of okay. Insert analogy here, or whatever. It's some. It's kind of a. You have to actually reset it in order to. Yeah. And let's see. I can't remember if this is. I think this is possible. Pause. No. I think I'm confusing this with other sequencing objects, but with routine, I think once you play them, off they go. There might be a way to stop a routine, or stop it and restart it, but I'm not sure off the top of my head. All right, so there's something else I wanted to. Oh yeah, very important. If you're doing an infinite routine, or even if you're doing a finite routine, you really got to put some yields in there, right? If I'm not going to do this, but if I ran this routine now, probably what would happen is there would be a really, really, really loud sound, and SuperCollider would become unresponsive. Because what we're asking it to do is make an infinite number of synths as fast as possible.
Yeah.
So this is a yeah, right. You just want to be as soon as you type the word loop or inf.do, stop what you're doing and just somewhere in that loop, just put $1.wait or something, just so you don't forget and get excited and I can't wait to hear what this sounds like. Yeah, it's a rite of passage. Yeah, it's a very easy thing to overlook. Yeah. And one more thing. This is something that I don't think I've really put in videos before, but this is a little a little tidbit from Nathan Ho's blog. It's when you are using routines to play synths, the more correct thing to do is to enclose synth calls and other things that produce sounds in s.bind. Yeah, so what this does, I mean, it's a little technical, but s.bind will take the contents of its function and basically bundle that into an OSC message with a precise timestamp. This is my incomplete understanding, so that the timing precision of the routine is properly transferred to the server. Because if you just play a synth without s.bind or s.make bundle, I think it's the timing precision is not guaranteed. I think there's this is taking advantage of the OSC protocol, specifically the fact that there is a high precision timestamp with the message. So it tells the server exactly when to schedule it at the cost of just basically delaying everything by a tiny bit. So when you play this routine, it won't start immediately. It'll be like an extra 1/10 of a second or something before it goes. But this is particularly useful if you are working with very small yield times, because you can try this yourself. Like if you just have a synth which makes like a little tick, like a tiny little click or something, and you want to do like 150 or 200 of them per second, if you try without s.bind, it'll be kind of like jittery and stuttery. It'll be like, but then if you put it in s.bind, then it should be very, very precise. So this won't sound really any different, I don't think. But you know, I've gone through many years of using SuperCollider without putting s.bind, but I think that's just because I'm working with big chunky yield times where like if this is off by a couple of milliseconds, it really doesn't matter too much. But if you are doing something and you want extra assurance on timing precision, then you should wrap your synth calls in s.bind. Just to, yeah. All right, so that is a routine as a sound generator. And so let me give you a different version of using a routine for something sort of totally different, but using the same mechanisms. And so in this example here, you know, we don't really, like I said, we don't really care about the values that are returned to us. We just care about what happens in between. But let's build a routine which is basically like a pitch generator or something that can be used for synths. So let's imagine we're working with the PVC sample, and we want to play that sample 1 octave down, and then we want to play it. We want to transpose it up by, you know, like maybe we want to choose from either 2, 5, or 7 semitones up. We want it to be different every time, right? So, so what we're looking for is like -12, and then, you know, maybe it gets transposed up by 2, and then maybe up by 7, and then maybe up by another 2. But we want this process to be uniquely generated every time. So we need to kind of, what we need is some sort of function that we can say, give me the next value, give me the next value, and have it remember where it is. And so it can sort of, you know, remember when it needs to go back to -12. You get the idea. So we can build this with a routine, essentially. So we'll say data function, or we'll say pitch function. So we're going to make another function, and we'll declare a variable for the note. And let's see, initially note will be -12. Right? We're going to treat this as just a transposition value. And then we want to say note equals note plus one of these values. Right? So basically, we have our variable, we do this, and then we just want to do this 3 more times and then kind of start over. And so we just want to say, okay, yield that value, right? So return, you know, spit out -12, and then it's going to apply this operation, and then we want to yield it again, and then we just want to do this 3 times, right? And then we want to do all of this forever. So I've just built our function which we're going to dump into a routine and call next on in order to extract these sample transposition values. We can let's go ahead and do that. Yeah. So now we're going to call next. And before we start actually evaluating this, let's imagine we are the interpreter and we are keeping track of pitch gen and the user has just said, give me the next value. So okay, well, let's start evaluating. I'll set aside this container called note and I'm going to enter a loop and note is going to be equal to -12. Oh, I'm supposed to yield the value. So here's -12. So that's what gets passed back to us. Right? And again, a routine is this special kind of function which remembers where it is. And so it knows it's right here. And so as soon as we call next again, it's going to keep going. It says, oh, here's a little 3.do iteration block. So it's going to say, all right, I'm going to pick a random value, add it to note, and yield that. Right? And then, so there it is. Happened to pick 7 that time. And then we call next again, and it's still stuck in this 3.do, so it's going to do that again. So it added 7, and then it added 2. Right? And now, when we say next, it's exiting the 3.do, and then it's exiting the loop, but because that's a loop, it's going to jump back up here and reset note to be -12.
And then repeat the do. Okay.
Right? So we just have these little chunks here, and if we happen to be somewhere in the middle of one of these cycles of 4 notes, and we reset that, then it's going to go back to -12. Right? And so now we can make a synth. In fact, I'm just going to copy it from up here. And put that here, and we're going to say rate : pitch gen dot next dot MIDI ratio, because right? Rate has to be a playback ratio, like 2 is an octave. So this MIDI ratio just does the conversion for us. So now we can just play this. So we get these kind of random arpeggios based on a whole step, perfect fourth, and perfect fifth. And then we get to combine these 2 usages if we want. We can just build another routine from a function. And this will just be a loop. And the first thing I'm going to do is put a wait time here so I don't forget. And just take this, copy it here. And that's basically it. And we'll say synth gen equals routine synth function. And now we can just say synth gen dot play. Yeah. So there we go. It's music, right? Yeah, so that's sort of the combo use of routine. Very, very flexible. So popular and useful that there is actually a method, a single character method, lowercase r, which when applied to a function returns a routine that contains that function. So that means instead of routine parentheses, putting a function in here, we can just say synth function .r. And if we do this, it is a routine, right? So it's just an alternative to do this. Right? Oh, it was somewhere in the middle, so it didn't start at minus 10. We can reset. We can even reset the data routine while this is playing. Like, I gotta stop this, play this. Oh yeah, the reason this doesn't work. Hold on. Gen. Because it has to be reset, right? Right. So you can reset and do it this way. But another good way to do this, if you don't like the whole dealing with reset, is you can just have this be. You can just play it. Stop, and then you don't need to reset. You can just declare that routine dead, and then just make an entirely new one. Right? It's just to maybe just yeah. maybe it makes a little more sense if I write it out like this. But this, this is just like, SynthGen is now this totally fresh and new routine, fresh off the assembly line, right? We can stop it if we want to make it again. Just make a new one, right? Just generate another one, right? Instead of dealing with the same one and rewinding and resetting, and so I find myself doing this actually quite a bit more, like when it's time to. In fact, this brings me to a point which I maybe should have started with, which is it's very important in SuperCollider and in general to make a distinction between a process that defines a sequence and a process that performs a sequence. And there's a really good analogy for this in the world of music, which is the score and the performance, right? Because the score is like a function. It's like one of these things, where like this doesn't actually make the music. These are just the instructions. But the routine is like, actually the drop of the baton and the music starts like that, interpreting the score to produce sound. So it's kind of like when we were doing function.play for just making basic sounds. The function defines that sound, and play produces the object that actually creates the sound. So we'll see this kind of distinction everywhere, just like something which defines the process and then the thing which performs the process. So, yeah, so that's why I'm sort of doing SynthGen and SynthFunction. And we'll deal with this again when we get to patterns, and it's a very, very important distinction to be aware of. So, but I really do like this this single character thing. In fact, what I usually do is just do the method and then the receiver in parentheses. So like this, just because instead of typing routine, you just type R. And yeah, it's one of the few single character methods in SuperCollider, so it's pretty useful. Oh yeah, so I was going to say we can reset the yeah. So it's all kind of like live. We're doing like a very tenuous version of live coding here. But yeah. Okay, so let me talk now about clocks and quantization. So what we've been doing so far is just treating this duration, anything that's yielded or weighted in automatic mode, as a duration in seconds. We've probably been thinking of it like that, and it's totally reasonable. But as I mentioned, this is actually a duration in beats, and it's only equivalent to seconds because the clock that drives this process is set to 60 beats per minute. And the clock happens to be an instance of a class called TempoClock. This is a scheduling mechanism. So basically you can schedule things to happen on a TempoClock. And TempoClock is convenient for a lot of musical applications because it doesn't just think in terms of seconds, it thinks in terms of tempo and beats and bars and stuff. So you can think of TempoClock as being sort of like imagine a DAW that doesn't have the vertical grids on it, and TempoClock suddenly, boom, you've got a whole metric grid, and so you can say schedule it on that beat, and 4 beats later, and on the next downbeat, and this and that. So that's really, really handy. When you launch SuperCollider, there is a default TempoClock which you can access through the default method, and its tempo is 1, and the TempoClock tempos are measured in beats per second instead of beats per minute. So that's why we see 1 here. So let's make, actually we can also check the number of beats that have elapsed. So the SuperCollider has been open for quite some time. This is maybe even from before I sat down to prepare for class. So it's just on, and it's just these clocks just run in the background, and you don't really have to. You generally don't have to worry about what the current beat is. It just kind of takes care of a lot of that for you. But let's make our own clock, right? So we'll do the same sequence, but we'll run it at a different tempo. Like let's pick a tempo here. So we can make our own tempo clock, and it needs a tempo again in beats per second. I don't think I've ever met a musician who thinks in terms of beats per second. We think in beats per minute, but that's fine. We can just divide that value by 60, and we've got beats per second. So if we were doing 60, let's do like 98. So we've just made a new tempo clock, and now if we say t.beats, you can see it's just begun, and it's counting a little bit faster. If you kind of track the integers, you can see it's going at 98 beats per minute. And So now if we, let's go get this here and just copy this whole chunk of stuff. Probably should have copied the pitch generator too. In fact, I'll just do that. That and put it here. All right, so we have our pitch function and then our routine that gives us the pitch values, and then our synth function which uses those, and then we make this. And we'll do, I do like this syntax a little bit better. So when we play when we play a routine, if we don't specify otherwise, then the first argument is the clock on which it should be scheduled, and the next argument is a quantization parameter. Basically, like, what on what beat should it be scheduled, when, what quantization granularity do you want? So if we don't specify anything, it goes on to the default tempo clock, which is why all of the weight/yield values get treated as relative to 60 beats per minute. So let's do that real quick. We're just saying, just be explicit here. Play it on the default tempo clock, and off it goes. Right? Same thing we just heard. But just to confirm, we still have this clock, which is still going at a different tempo in the background. So we can just say, play it on T. And this is so much easier than like having to do the mental gymnastics of getting what exactly is the duration of an eighth note at 98 beats per minute. Nobody wants to deal with that. That's why TempoClock exists, so we don't have to think about it. So that's very easy. And in fact, you can change the tempo of a tempo clock at any time while something is playing on it. So that looks like this. So we can just check the tempo like this. Right, there it is. And we can set it to 92 beats per minute. Yep. All right, so that's all very flexible. All right, and let's talk about quantization, I think. In order to show that effectively, what I'm going to do is write a small function that just posts every beat in the post window. I've done this in other videos. So we're going to make a function that just says t.beats.postln, and then we're going to return the number 1. You'll see why in just a second. And then we're going to say, before we do this, I know I'm all over the place today, but if you hit command period, as I just did, that has a side effect of killing all the tempo clocks. So that tempo clock we made, T, is now gone, right? So if we try to play this on T, it's just not going to work. We would need to create it again, yeah, which is annoying. We don't really want to have to do that. I think the default tempo clock is still alive because it is set to be permanent. Tempo clocks, all clocks have I don't know about all clocks, but definitely tempo clocks have an attribute called permanent, which by default is false, which means command period will wipe them out. So let's remake our tempo clock, and we can just, in the process of making it, we can say, by the way, you're permanent. Right, so there we go. And now if we do beats, it's been born again. And if we command period, has no effect.
And default is overrunning by itself.
What's your question?
And the default is also continuing.
Oh yeah, the default is always there. I mean, we could, I believe, make the default tempo clock non-permanent, and then command period would destroy it. But then we'd have all sorts of other problems, because every routine we try to play without specifying a clock is going to try to go to the default tempo clock, and it's going to be a mess, right? Yeah, I don't recommend messing around with the default tempo clock. It's just there as a convenience, basically. Yeah. So we now have this one, which is permanent. So we have this function, which, when evaluated, posts the current beat and also posts the number 1, as I said, you'll see in just a second. And so then what we're going to do is schedule a sched abs, which is short for schedule at the following absolute time. And so the time, we need to provide a beat, and we're just going to say t.next bar. And this just gives us the upcoming beat number of the next bar. And by default, TempoClock thinks in terms of 4 beats per bar. I'm going to refer you to tutorial 29 if you want a little bit more info on exactly, like other things, how to change beats per bar and stuff like that. But we are just going to schedule a function which evaluates post. So when we run this clump of code, we define our function that's responsible for printing information, and then we schedule it on the TempoClock to begin on the next bar, whatever beat that is. And on that beat, it's going to perform this function, which evaluates the post function. And because this function returns a number, the TempoClock will interpret that as, oh, I'm supposed to reschedule this function that many beats later. So by finishing this function with a number, it has the effect of causing it to be rescheduled. Let's see if this works. Yeah. All right, so now we just have a little process which is just posting these beats. If I change the post function to be empty, then that basically this function suddenly evaluates nothing, something which does not return a number, and so it takes it off the scheduling grid, basically. This is if this doesn't make 100% sense to you, don't really worry about it. I'm just doing a visual aid so that quantization makes more sense to us. Right? So let's grab this stuff again. Yeah, maybe copying and pasting not totally necessary, but we're going to do it anyway. So instead of just playing on T, we are also going to just make sure I'm doing the right thing here. Yeah, I'm pretty sure that we can just do these 2 arguments, but I'm not 100% sure. I think it's just these 2, but we're going to do it this way anyway, just for extra clarity. So it's going to be on T, which has a tempo of 98 beats per minute. So here's the way quant works. If you just give it a number, like 1, it is going to, this is interpreted as the beat, the quantization granularity, which means the unit, the beat unit on which it will be based. So basically, this is going to play on the next beat, whatever that happens to be. If we do 4, it's going to be scheduled on the next multiple of 4 beat. So that's going to be 400 if I time this correctly. And it's a little bit weird because it's a 5 tuple, right? Because it's doing 1/5 of a beat. So let's stop this. Yeah, that was a little bit. Let's do these I guess these are technically, if 1 beat is a quarter note, these are 16th notes. Let's do half notes. 8th notes, sorry. Yeah, I said half because it's 0.5, but it's if we're in 4/4 or 2/2 or 1/1, I mean it's all kind of relative. So this is a half of a beat, which you can think of that however you want. So yeah, let's try this again. So now I'll try to get it on 480. Yeah. So that is what quant4 does. Yeah. So you can stop that. The actual file, the class that's being used indirectly by putting the number 4 here is something called quant. And so there's actually a couple of different values. There's quant, phase, and timing offset. We don't care about timing offset right now. That's like an internal thing for special cases. But phase is kind of important. So phase is a beat offset relative to the target that the quantization granularity specifies. So this, like let's say we're going along 4 beats per bar and quant is 4. This means that no matter what we do, it's always going to come in on the downbeat. But what if we want something to come in 1 beat pickup or something like that, like right before the next downbeat, 1 beat ahead of the, that's what phase is for. and I have to remind myself, okay, so yeah, +1 is 1 beat later, -1 is 1 beat earlier. Think of it like on a timeline, basically. -1 goes to the left, so it's earlier. And so we have, the one option we can do here is just an array. Right? So this will first identify the next downbeat, and then it will try to put it on the beat right before it. Right? So if I go for 632, it should come in on 631. Yeah. Or you could also do quant, like an actual quant object, right? This is like the official way of doing it, but if you want to put in multiple numbers for quant, you can just do an array containing those numbers. And if you only care about the first number, you can just do an integer, and then you're all good. So this is a really important technique for getting multiple routines to play in, synchronized fashion. So if you want, you have that's what I was doing just a little bit before class, before I started recording with my sort of wacky PVC thing. It's just you can lock them all together. So could try to build something really quick here. Why don't we just take this? Let's just make a say R0 is going to be a routine which is just picking randomly from these three numbers, and we will play this on t quantized to 4. Right? Okay, so we'll do this one, and maybe adjust the amplitude just in case we get a little rowdy here, and do this. Okay, right. And then we'll just divide this by 2, right? Make it down an octave, but of course they're going to be totally random. And we'll add the perfect fifth as well, and do this. Yeah. And then we'll divide by 4 and make this a little bit louder because I think it's going to be kind of quiet. And make this one fast again. We've got to call this R2, I guess. I'll stop that one. We'll do 0.75, I guess. And well, let's make the release really short. And the sustain 0. That's a little better. There's a little 2 against 3 thing happening with 0.5, 0.75. Yeah. And make one more. Yeah, all right, and then we can, let's do iteration to just stop all of these. We can stop them one by one, but that's, this is do, yeah. All right, and then we can make this into nothing, and how do we get rid of tempo clocks? I think we just stop them, yeah. So now that one's dead, right?
Wow.
Yeah, so a little live coding session for you at the end. A little baby live coding session. Okay, so that's routines and tempo clocks and quantization and all the fun things you can do with them. I'm working on tweaking the homework assignment, but we're also going to try to cover patterns. So that'll be the subject of the class next week. So we're talking about all the sort of basically when we built this where did it go? This thing, for example, like we're thinking about a particular sequence of numbers that we want to do. Here, this is kind of like a build it from scratch approach, but patterns a lot of value patterns encapsulate very common things like pick a random value, do things in sequence, add a number, multiply a number. It just they're little prepackaged units that save you the trouble of having to do this. So this kind of stuff becomes like a one-liner. And then we'll also talk about p-bind and events as a way of using patterns to create sequences of notes, which I think is kind of a nicer approach than this, although routine is very useful as well for lots of different reasons. All right, so that's it. I'll pop this in the library if I can sometime tomorrow, and I'll give you an email whenever the next homework is out. Oh, and the take-home midterm will be assigned 1 week from today.
Oh, yeah.
Oh, we have a midterm.
Yeah,
We have a midterm.
it's going to be a 24-hour take-home midterm. You have the whole internet at your disposal, notes, videos, whatever. You just can't work with each other and can't talk to the TA. So, that's it. All right, so that's it, and I'll see you next week.
Thank you, Eli.
Mhm.
Yeah, thank you.